Compiler construction 12. So last time we introduced the R part of the new extensions to our language that do heap allocation. And what we'll do now is we'll cover kind of the back half of it. Yeah. So the first thing we need to do is we need to update the resolve complex pass. That's the RCO thing that goes through our programs and structures them into, arguments, um, you know, complex expressions and expression forms. But this is actually quite easy. So collect will just be an expression, and then allocate will also be an expression. Now, when I say expression, that means a complex form. A global is just a new kind of argument. Unit is an example of an argument. Vector ref would be an expression. Remember, when I say expression, that means a complex. Complex, complex, complex. And recall that complexes, they're the right-hand sides of let. So that means that if something is a collect, then it has to be given a variable. Allocate needs to be given a variable. Vector f needs to be given a variable. And then vector set will also be an expression / a complex. Now, one thing that you can do inside of your RCO pass is that you're going to have lots of examples of let a variable equal a complex where the type of this thing is unit. Now, if the type of that thing is unit, then that means that we know that V is actually a unit. So in that case, what we can do is, recall that our structure is basically something like we have, a let of a variable equal a complex inside of another expression. If we wanted, we could explicitly make a sequence form where we have the complex and then the expression. And what we could do is we could notice that whenever the type of a C is unit, then we could transform it into this and then substitute the actual unit value for this V in the rest of the code. And that's going to make it so that units never actually appear in the code at all. Like, there is no value that is a unit, so we don't even need to have it represented in the compiler in any meaningful way. It's just sort of a convenient notation for talking about what the results of values are that you can't look at. I recommend you doing that, but I'm not going to actually I'm not going to assume that you actually do that. It's just kind of a convenient thing to do. Okay, the next thing that we need to do is we need to talk about the changes to the econ pass. And the changes to the econ pass mean that we're going from the C1 language to the C2 language. Let's talk about the changes to that. So arguments are going to be updated. There's going to be globals. And I think of globals as being like strings. There's just you just name some global variable as a string. Then there's going to be units. And every time you have a variable, you have to be able to figure out what its type is. So either that means that they're explicitly annotated, or there's this background function that you can call. You can go look at this mapping and figure out what the type is. Expressions are modified in the following way. There's a new allocate expression, which takes a number and a type. And then there's also a vector ref, which has an argument and a number. And then finally, there's a new kind of statement. And these new kinds of statements are when you have a collect of a number and when you have a vector set of a arg, number, and arg. Okay. You, of course, will want to update your interpreter for C programs to deal with these. And you basically just use the same strategy that, as I mentioned before, where global, just reads off very particular fake values, allocate returns a vector of the appropriate size, vector f and vector f look at it, and collect does nothing. Okay, so now let's talk about how econ works. So econ for global and unit is trivial. You just identify those arguments and convert them. It's really allocate, collect, vector ref, and vector set that are more interesting. But even those are pretty straightforward because vector ref and allocate are just other examples of expressions because they will appear on the right-hand sides. Really, it's only noticing that you don't need these variables. So basically what you're going to do is you're going to say that when you call econ and you give it a let of an x equals allocate of a number and a type inside of some body, then what you're going to do is you're going to turn this into a sequence, because remember, sequence is what like C tails are either a sequence with a statement or a return. So it's a sequence of the new, in this case it would be a set bang of x and allocate of the number and the type inside of the econ body. That's the obvious case. And then what about when we have a vector set or vector ref would look just like this. But what about when we have let of blank equals collect of some number in the body? This is the case where you generate the sequence of directly using the collect form and then the econ body. So we don't even bother creating a variable for these things. That's all I'm saying. Okay. So when you do so you've done econ. Now the next thing we need to do is we need to do uncover locals. So basically the way that uncover locals used to work is it would just go through the C program and look at all the set bangs. And it would just say, okay, well, here are all the variables. So basically its old answer was information about the names of variables. Names of variables. And the reason we had that list of names of variables is so we could use those to populate the interference graph. Well, now we actually need to know not only the variables, but their types. But it turns out that if you followed my advice before, you actually just already have that. So uncover locals essentially doesn't need to even do anything anymore because you already have a mapping of variables to their types. But that's what we need. What we need now, the new thing, is variables and their types. And their types. Okay, so if you made it so your type checker returns gamma, then you just preserve that information across the previous passes, and then you're done. Okay, so suppose that that's what you actually have, then you're good to go. On the other hand, if instead you did the technique where you individually annotate every part of the program with their type, then in that case, uncover locals has to go through and actually gather all those together. So you can do either one of those. I think that returning gamma is the easiest thing to do. Okay. So the next thing that we need to do is we need to start talking about how to modify the X language. All four. So we're going to be going from X1 to X2. And here's what we're going to do. We're going to modify args in the following way. We're going to have a new one, which is a global, which is going to have the string. And we're also going to have a way to refer to a type as an argument. And then we're going to add a new instruction, which is the Leia Q instruction, which takes 2 arguments. Okay, now what are these things? This right here is called the load effective address. And what it does is it loads the address of this into that. Okay, how do we use this? Once you understand how you can use it, then it'll be a little bit more clear about what it really does. Essentially, how this is going to work is that what's the right way to say this? This argument right here has to be a memory reference. So it has to be an offset somewhere. And if you just did a move queue of a memory reference into that one, what that would do is it would read the value there. So imagine that I have in memory location 5, inside of 5, I have 17. Well, if I do a move queue of that location into 17, into some other thing, then I'll get 17, because I would have moved the contents of this memory into this other place, and I get 17 there. If I instead say load effective address of this thing down to there, what that does is it installs 5 into there. Now you might say, why are we putting 5 into there if I already had to know that it was 5 in the first place? Well, here's kind of the real reason that this is interesting, is that that thing right there can be any memory reference. And since it can be any memory reference, that means that it can be relative to like the instruction pointer, let's say. And this is kind of a detail about how assembly programming really works. You typically can't actually get access. You typically can't actually get access to the real addresses, because when the operating system loads your program into memory somewhere, it doesn't tell you where that's going to be. So that means that you basically need to make it so that you can figure out where it is going to be when it actually gets loaded. So, like, basically, like when you load your program one time, maybe a global variable is going to be an address 17, but when you load it another time, it's going to be an address 2000, and another time it's going to be 4000. Well, how are you supposed to know? Well, the way that you know is you basically code in to the assembly that you don't reference 17, you reference 1000 away from this instruction. And then wherever that instruction ends up being put in memory, you can then subtract, or add whatever to get to the actual pointer that you care about. All this is really saying is that effectively LEAQ is the way that we do like the @ sign in C. It's like the @ sign in C. It tells us the address of something, not the thing itself. Okay. So now, so how are we going to actually compile each one of these things? And sorry, not right. How are we going to compile them? How are we going to emit them? When I say emit, what I mean is a way to take these things and turn them into actual assembly. So LEAQ is simple, right? You just print out LEAQ. But global and type, those are the complicated ones. Basically, here's how it works. When we emit a global of a string, what that turns into is it turns into that string %RIP. So that is going to be, that's the way that you reference a global variable. Now, it might be the case that you might have to add an underscore right here. And this string has better be a variable that your runtime system exports. If you don't remember, a C program exports all variables that are not declared as static. So everything else gets exported. Okay. Now type, that's the more interesting one. How are we going to emit a type? Remember, here, like an example of this would be like, how are we going to emit type vector S64 bool S64? What does that even mean? Essentially what we need to do is we need to make it so that we need to make it so that our program, so that our emitter of assembly code produces our program, and in another place it produces data. And when I say data, I mean like concrete, actual like numbers. So here's the strategy that I recommend doing. When your emitter sees this, what it does is it sticks in a reference to type 27% RIP. Okay, just like for a global. But now, what is type 27? On the side, what it does is it makes a little note to itself to put in type 27 is a label, and with the contents of that label is the following: dot quad of, let's say, 3, dot quad 3, dot quad 1, dot quad 2, dot quad 1. And then all this stuff goes in the read-only region. It's actually called a section before the code. So it's called RO data. Okay, if you haven't done a lot of assembly program, I'm talking gobbledygook to you. Okay, if you actually look at the assembly programs that you generate, what you do is you generate a listing of, like assembly instructions. And those assembly instructions, they say stuff like move queue and whatever, and they have labels like main or, begin or end or whatever. Well, one of the things that you can do is you can tell the assembler that I don't want you to output the instruction move queue. I want you to just literally put into my code the number 3. And the way that you do it is you do dot quad and then whatever number you want to do. And this is going to insert directly into your program a 3. But obviously you have no idea what number corresponds to what instruction you want to do. So you're basically never going to use these quad instructions in the the code part of your assembly program. However, one of the things that you can do is you can tell the assembler, like, this particular region of the assembly output is just pure data that I promise I'm never going to modify. And the way that you do that is you write .ro data. So when you do .ro data, and now everything after that will never be changed. And there can be labels inside of there. And so what you can do is you can say, like, when you see a type, you say, this is type number 27, and obviously you have some counter somewhere where you keep track of how many different types you've seen. And then for each one of those, you have this little format right here. Now, what does this format mean? Basically, what you're going to do is you're going to have in your runtime system a mapping that's going to say 0, that right there is unit. 1, that is S64. 2, that's bool. And then 3, that there is a vector. Okay? So this 3 right here says this is a vector. This is a vector. So type 27 is 3 a vector. Now what's this 3 right here? That 3 is saying it has 3 elements. 3 elements. Then we need to know that this one is an S64, this one is a bool, and this one is an S64. So now what's going to happen is that this type is a pointer to that particular address. And it's a pointer because you are going to use LEAQ on it later. We haven't done that yet, but that's what you're going to do. So it is some particular region of your assembly code. And so you're going to take that address, you're going to LEAQ it, and then bam, now you're going to get pointer to this particular thing. You're going to pass that to your runtime system, and your runtime system is going to look at the first number, and it's going to say, aha, it is, it's a vector, because that's number 3. And then because I know it's a vector, I know that I'm going to look at the next number, and it's going to tell me how many elements there are. Then I'm going to look at the number, then if it said there were 3, I'm going to look at 1, 2, 3, okay, aha, there we go. There are the 3 different things. So that's kind of the idea. Okay, and so that's how we're going to emit our program, our X programs. Now, the best thing that you should do is you should make it so that every type occurs only once. So if like vector S64, bool S64 occurs many times in your program, then you should only generate type 27 once. If you want to be lazy, you could generate one for each occurrence, but don't be a bad person. Don't do that. Okay, now what we're going to do is we're going to talk about how to turn the pieces of our the pieces of our really how to do select, how to actually turn C stuff into X stuff. So we want to talk how to go C to X. This is the select pass. What's on off screen? There we go. By the way, we're like halfway through the class, and you may say to yourself, like, I never felt like I was writing a compiler. I felt like I was just doing all these like random little bitty pieces. That's the whole point, right? The whole point of the structure of this class is that you're writing a compiler by me handing you the architecture. It's like, this is the architecture, and here are like the fundamental pieces that you're going to do, and just build these. Now, obviously, I've kind of not really specified every little thing, so you're going to have to figure some details out yourself. But by doing this, you then can really understand really how it works. But you didn't have to have the complexity of designing the compiler. We could have imagined a totally different compiler class that was focused on like the big picture organizational ideas. And in a class like that, we might talk about like, oh, well, there are bottom-up transformations and top-down ones, and here's the different kinds of algorithms like that. I feel like for me, what I want you to get the experience of is like, I wrote a real compiler that like really does something. Okay, that's what I'm trying to get you to feel. Okay, now let's talk about select. So when we select an argument that is a global of some string, well then we'll just turn that into the global of that string, which remember is gonna turn into that string %RIP. Now what if we get a select A of a unit? Then we're just going to turn that into 1. Now, as an aside, remember, I told you that we could actually arrange things so that unit values never occur, except as arguments to vectors. And what we could even do if we wanted to is we could throw them out. And what do I mean by throw them out? What I mean is that, like, imagine you had a vector which was a vector of a bool, and a unit. Well, you know that if you ever actually looked at that unit, it would be the unit value. And if you ever modified it, you can only modify it to the unit value. So we can actually imagine modifying all vectors to just get rid of the unit arguments at some point in the middle of the compiler. So we actually would never even need to have unit values. That's kind of a fun thing that you could do. All right, next, what if we're going to do a select E on allocate of a number? Okay, here's what we're going to do. What we're going to do is basically what we're going to do is we're going to call a function. Oh, sorry, allocate takes the number and a type. Don't want to forget that. Okay, erase that. All right, takes allocate, type. Okay, now what is this going to do? Essentially what we're going to do is we're going to look at the free pointer and then grab some space and then install stuff into it. So here's what we're going to do. Oh, by the way, remember select E takes a destination that is going to put the result of this expression in. So here's what we're going to do. We're going to move Q, the global free pointer, into the destination, because we're going to take over that address. We already checked, by the way, that address that address has enough space, because that was what expose allocations did. Then what we're going to do is we're going to do an add Q of the constant 8 times 1 plus this number. Okay, that number, by the way, is a constant. We know exactly what it is. We're going to add 1 to it, multiply it by 8. What's going on here? Well, we need that number of words, that number of slots in the vector, and then we need one more for what's called a tag. A tag is going to be a pointer to the type so that we know what kind of type this thing is. Our garbage collector needs to know that so it can walk across it. So we're going to add that amount to the global free pointer. That right there is us allocating the space. Once we move the free pointer to the destination, we just claim that, and then once we increment it, now we've taken over that amount of space. Next, what we're going to do is we're going to move Q, the destination, into RAX. Then what we're going to do is we're going to load the effective address. We're going to load the effective address of this type, that type right there, and we're going to put it inside of %R11. Then what we're going to do is we're going to move Q R11 into RAX 0. Okay, now what's going on here? Okay, what we want to do is we want to make it so that the pointer to the type is installed in the first cell of destination. So how can we actually make that happen? Well, we can't write down LEAQ type. So here's what you might think we could do. We might want to do something like LEAQ of the type into the destination 0. Now, why can't we do that? The reason we can't do that is because we constrained our implementation so that you can only have offsets into registers. And destination is not necessarily a register, it's probably a variable. So that means that we can't write this. So that's why we have this move Q down here of move Q 11 into %RAX 0. Okay, now here's the next thing. Why don't we do LEAQ type into %RAX 0? Well, we can't do that because we know that type is a memory reference, and we know that this is a memory reference. So therefore, we would know that there are two memory references there, so that's not allowed. So that's why we choose R11. You could obviously choose any variable, any register that you wanted. And the reason that we move destination into RAX is just setting things up so that we're allowed to dereference it like that. So effectively what this is going to do is it's going to make it so that we can't really use RAX or R11. I mean, this will emerge naturally out of the way that our build interference is going to work. This is going to basically make it so that those registers are sort of taken off the table because these things may occur all over the place. Okay, so that's how we're going to select E of an allocate. What about when we do select E of destination vector ref? So vector ref is going to have an argument and a number. Okay, what are we going to do there? What we're going to do here is we're going to do move Q of the select A of that argument, that one, into RAX. Then we're going to do a move Q of %RAX, and then we're going to do 8 times 1 plus the number, and we're going to move that into the destination. What's going on here is that we're making it so that that argument becomes RAX, and then we dereference the appropriate part of it and we put it in the destination. This, by the way, could potentially generate two memory references. So yeah. And by the way, you may not want to use RAX because RAX is how you break memory references. Maybe you'll want to use R11 right here. Yeah, let me change this to R11. R11. So you just pick some other register. Okay. Then what do we do for collect? When we do a select S of collect and a number, actually, you know what? Let's do collect second because it's more complicated. What if we do a select S of a vector set of the vector argument, the number, and the new value argument. Okay, what do we do there? What we do there is we're going to move Q of select A of the vector argument, and we're going to move that into Rex. Then what we're going to do is we're going to do a move Q of select A of the new value argument. We're going to move that into R11. Then what we're going to do is we're going to move R11 into %RAX 8 times 1 plus the number. Okay, and so that's going to do is it's going to use RAX as an as a base pointer, offset it by 8 times 1 plus n, and move R11, which is select NA, into there. All right. By the way, what's these 8s for? Those 8s are because all the elements of vectors are always words, which are 8 bytes. Okay, 12, 7. What's next? Okay, so now we got collect. So select S of collect number. All right, this is going to be kind of complicated. Basically what we're going to do is we're going to call a function. We're going to do call Q of collect. And collect is going to be a function that we implement inside of our runtime system to actually run the garbage collector. It's going to take 2 arguments. One argument is going to be how much memory we need. So we'll move, move Q of $number, and we'll move that into %RSI. RSI, by the way, is the second argument. But now we need to give another argument. And to describe what this other argument is, I have to tell you something about how the garbage collector is going to work. And it's kind of complicated. Basically, what we need to be able to do, so every garbage collector has to be able to say, when collection happens, what variables can be referenced right away, because this is tracing. By the way, I'm not really explaining in garbage collection in detail. We'll talk about the algorithm in a moment, but the idea of garbage collection, I'm relying on you taking the organization of programming class to really understand it. So one of the things that you need to do, right, with garbage collection is you need to have the root set. So essentially, we need to tell collect what the root set is somehow. Now, where could things possibly be? Well, things could be inside of registers, or they could be on the stack. Those are the 2 places that things could be. What we're going to do in our compiler is we're never going to put vectors, that is, things that have pointers inside of them. We're never going to put them in registers. We only put them in registers temporarily right before we read them. That's what's going on with this vector set and this move Q and this move Q. This argument right here and that argument, I promise you they will always be memory references, because they're always going to be in memory somewhere. Okay, so because we're not going to have them be in registers, that means that we don't have to tell collect about any registers. The next place that they could be is they could be on the stack. And if they're on the stack, we need to tell collect some way for it to go look through the stack and find things that are pointers and find things that are not pointers. Now that's really a pain to do. So we're going to cheat. The way that we're going to cheat is we're going to have it so that there's 2 totally different stacks. There's one stack that is for normal variables. These are like numbers and booleans. And then there's a totally separate stack that is only for things that are pointers. And so because there's a totally other stack for things that are pointers, that means that all we need to do is tell collect where that is right now. And the way that we'll do that is we're going to move Q we're going to move Q, the root stack register. That's what we're going to call it. We're going to call it the root stack register. And we're going to move it into %RDI, which, by the way, is the first argument. Now, what is the root stack register? The root stack register has to be a register that is call E saves. It has to be call E saves because collect has to be responsible for restoring it back to the previous value. So it just can be anything there. I recommend R15 because that's our call E saves register, and it's the last one. Okay, so now we have to talk about all of the other little things that we do to all the other little parts of the compiler. And the runtime, of course. Oh, and you know what? I should say something about interpreting these new changes. So, you'll interpret global, right, by just having these global variables. Type will be really easy. It'll just pull off the type. Load effective address, we know that it will only be ever used on type, so it can just move the type into there. And then you'll have to simulate the function calls for, collect. For collect. Okay. So 12.8. 12.8. Okay. So here are the new things that we need to do. We need to say how live is going to change. How that's the thing that collects the live sets. We need to talk about how we're going to update the conflicts, the interference graph. We need to talk about how we're going to assign homes. We need to talk about how we're going to patch instructions, and we need to talk about how we're going to update main. So those are the things remaining. And each one of those is little. Okay, here's what we're going to do to live. The only thing we need to do for computing the live after sets is we need to say what happens with LEAQ. And LEAQ is just like move. It reads from the source, it writes to the destination. Boom, we're done. Okay, conflicts. Conflicts, we need to treat LEAQ just like move. Just like move Q. All right, good. What else do we need to do? The other thing that we need to do is we need to make sure, we need to update the way that we handle a call queue. So we need to update what call queue does. What we used to do with a call queue, is that we used to say, for all of the variables that are in the live after set of this instruction, and for all of the registers that are in the caller saved registers. Okay, so for all the live after, everything in the live after set, for everything that's caller saved, we want to add RV to the interference graph. Now, our new rule is going to be bigger than that. Our new rule is going to say, do everything the old one did. Okay? And do one more thing, which is that for all variables that are inside of the live after set, where when you look up in gamma that variable and it is a vector, then in that case, we're also going to add and for all our, wait, hold on, I'm getting lost. Okay, so what we're doing is we're saying that everything that's live after this caller saves thing, we need to make sure, everything that's caller saved. Okay, yeah, sorry. Okay, So for all the variables that are in the live after set that are vectors, we need to add additional interferences for all of the registers that are in the call E saved. Notice that there's an E right there. We're going to add RV to I. Okay, what does this do? What this does, this thing right here makes it so that no variable that is live at this point can be caller saved. Because all the ones that are caller saved will get overridden by this call. And what this one does is that all the variables that are alive, that are vectors, can't be callee saved either. Therefore, they can't be in registers. They have to be on the stack. Yeah, that's the idea. Okay, so that's the change to live and the change to conflicts. Let's flip the page and do assign. 12.9. Here's what we're going to do to assign. So it used to be, this is the old rule, that variables either go to a register or the stack. So if they're a register, that means that they were, less than 13, their color was less than 13. And if they were more than 13, then they would turn into, RBP, and then we would put in, 8 times whatever the color was minus 13 or something like that. Okay, that's the old rule. Here's the new rule. The new rule is going to split up the arguments, into 3 sets. So the things that are registers, that's set number 1. Set number 2, vector variables on the stack. And then the third set is non-vector variables. Non-vector variables on the stack. The registers, they just become themselves, R8 or whatever. The non-vector variables on the stack, they're going to turn into RBP 8 times, which number they are. Now, what do I mean by which number they are? What I mean by that is that, we're going to look at the, what's the right way to say this? So, we're going to look at all the colors that come back, and suppose that there were 10 registers. Then the first 10 things are always going to be registers. So that's this category. But everything greater than 10 is either is going to be on the stack, so it's in one of these categories. And if we look at the thing and it's not a vector, then it's going to be based on RBP. So let's say it's the 12th thing. Well, in that case, we'll take 12 and we'll subtract 10 from it. We'll get 2. And that means we'll do RBP 8 times 2. But if it's a vector register, then instead we'll do the root stack register, and then we'll do 8 times which number it is. Now notice that these two things will overlap with one another. And so we actually may end up using more registers than we think that we have to. And what am I trying to say with this? Imagine that we have in the conflict graph variable x and variable y, and x is a vector and y isn't. Then we might say that they conflict with one another because they're live at the same time. But because they both end up being after 10, that means that we know they're going to be installed in the stack, but one's going to be installed in the normal stack and one's going to be installed in the root stack. So that means they don't actually conflict. So this is an example of some like conservatism in our register allocator where it's going to do a slightly worse job than it would otherwise. Okay. Patch, as I mentioned before, LEAQ is like move. And so LEAQ is like move. So that means that you can't move from one memory to another memory. But it turns out that we guarantee that we never generated code like that, so you don't really need to worry about that. Okay, 12.10. The last thing is how we're going to change main. Remember, what main does is it generates our function preamble and postamble. So our begin, the begin block. So here's what our old begin block was. So inside of begin, here's what we used to do. What we used to do is we used to push all of the used call E saved registers. Then what we did is we moved RSP into RBP. Then what we did is we did a subtract queue of how much stack space we needed from RSP, and that allocated stack space. And then we jumped to the body. Okay? What we're going to do is we're going to insert some new code right here prior to the jump. What we're going to do there is we're going to subtract queue the root stack space from the root stack register. Because now we have these two different registers that are basically like stacks, so we need to allocate the space for that. So this SS is how many normal variables there were, and this root SS is how many vector variables there were. Then what we're going to do is we're going to call queue of initialize. Initialize. Initialize is going to initialize the garbage collector. And it's also going to install the global variable. It may update the. Oh, sorry. I need to rearrange these things. Look at that, I missed the queue somehow. Okay, sorry. What we need to do is we first call initialize. Then what we do is we move queue the root stack start into the root register. And then we subtract the space. So this initialize, basically what it's going to do is it's going to call malloc and get space for us. All right, 12.11. What does main do for the end block? It's basically going to do the opposite. So the old code is that it would do a move queue of RAX into RDI. Then it would call queue of printint or print bool, and then it would be done. What our new code is going to do is we now don't know what type it's supposed to be. Sorry, it might be an int, it might be a bool, or it might be a complicated vector. So instead we're going to do an LEAQ of whatever the final answer type is, and we're going to move that into %RDI, which is the first argument, and we're going to move Q RAX into RSI, and then we're going to call Q print value, where print value is going to be able to look at the type and figure out how to print it. This answer type, by the way, is the final type of the whole program, which we will have kept track of this whole time. Okay, so we've now covered the extent of the compiler. Now, what you should do the first time you do this is you now have to implement inside of your runtime system, you have to implement collect, initialize, and print val. So those are the three things that you need to do. So my advice is to make it so that what initialize does is nothing. It just makes the free pointer like 0 or something like that. Then what you do after that is you make it so that initialize doesn't do anything. Then what collect does, and collect, by the way, will always be called because your initialize never sets the free pointer to anything useful. What collect does is it's just going to malloc some memory, put that inside of the free pointer, and then be done. And so what that's going to do is it's going to make it so that allocate is just going to use that space that you just asked for. And you're going to make it so that you just leak memory. You never do anything to it. And then your print value function, I mean, you can just go implement this. You got to you have to have it look at the pointer for the type and figure out what it is and figure out how to print it. You'll need to make it so that you actually print out the vectors. And so what we'll do next time is we'll talk about how to implement print value, anything complicated about it, and how to really actually implement the garbage collector runtime system. So that'll be fun. So that'll be next time.